Okay, the first important bit is to read that first sentence. So for me, it's metals and non-metals. Tells me straight away, periodic table, I'm going to be talking about that. What do I know about metals? What do I know about non-metals? It then says that shows a figure 1 outline of a periodic table. For me in my head, I know they've shown me that staircase, so I know straight away D is my non-metal, and everything else I know are my metals. Like, I haven't looked at the question. I'm doing that straight away because that's going to help me, I'm sure, later on. And then it says the element Q is a dull solid. Well, dull solid, dull tells me two things. One, it's not shiny, and solid tells me its melting point must be higher than room temperature, and that's what it tells me. It's a melting point. That's that physical property that I can measure above room temperature. It also tells me it does not conduct electricity. Well, it being a solid, that doesn't necessarily help me, because if I look at what I've labelled on my periodic table, it could be a metal, it could be a non-metal, because I know solids are in both of those, but does not conduct electricity. Well, metals do conduct electricity, so I know it must be a non-metal we're talking about. And then, which section of the periodic table in figure 1 is most likely to contain element Q? Well, I've already labelled my periodic table, so that's going to help me out. It can't be A, because that's a metal. Can't be B, cannot be C, they're all metals, so therefore it has to be D, because everything else is a metal, and it's only section D is a non-metal. If I then move to question 1.2, element R forms ions of formula R2 plus and 3 plus. Well, I'm looking at ions and I straight away think map nan. Well, metals are positive and non-metals are negative. Well, I don't need the negative bit, so I'll get rid of nan and just think map. Metals are positive. So I know it's not going to be section D, because that's a non-metal straight away. So it's going to be between A, B, and C. Well, I then look at the ion charges, 2 plus. Okay, if I look along my groups and imagine groups, section A is going to be group 1 and group 2. Group 1 is always going to have a positive 1 charge, and group 2 is always going to have a positive 3 charge. Well, a positive 2 charge. And it tells me R2 plus, that could be section A, but then it says R3 plus. It cannot be section A, because that's only plus 1 or plus 2. So I know, therefore, that it can't be section A. Now, if we go to section B, we know our transition metals. They're all over the place. Okay. If we go to section C, that is group 3 to start with, then 4, then 5, then 6, 7. But group 3 only has a plus 3 charge, and this tells me it can be plus 2 or plus 3, so therefore it cannot be C. It has to be B. Okay, that's going through a method of getting rid of the wrong answers. You could think, actually, it's got an ion charge of 2 plus and 3 plus. The only group of elements that can have two different ionic charges are transition metals. So it has to be group B or section B. Now, 1.3 is a little bit more, because it's not just a tick box. It says give two differences, and straight away you've got that important word there, two. How do we know it's important? Because they've put it in bold. It must be important if they've put it in bold. And then it's differences, not similarities, differences. And it's crucially between the physical properties. So we go right back to the beginning of this question. They were telling us physical properties, or they told us physical properties for element Q. Okay, it's not useful for group 1 and transition elements, because that was in section D. But they're linking these physical properties of things we can see, things we can measure, things we can observe. And as part of that, we have group 1. Well, group 1 elements, those are our alkali metals. We know when we put sodium or lithium or potassium into water, we've got this list of all these different things. It's not giving us list, it's saying give two differences. So if I think through to some of those things that I know that it does, I can say that it floats, or alkali metals float. Well, what is the physical property to do with floating? That's to do with density. I know that sodium melts into a ball, okay? What's the physical property? That's melting point. Okay, so we've got 2 straight away already from there. And we could have more. We can say, we can cut these with a knife. That's soft. That is the physical property, it's soft. Okay, those are 3 straight away we could use. Now, as part of that, we could use the word malleable because they're metals. But as we've written it here, that's not a difference. We've just written physical properties down. We have to say the difference, and it's the difference between group 1 and transition metals. So we can't just write density. We can't just write melting point or soft or malleable. We actually have to do it differently than that. Okay, we've got those ideas in our head of density, but this time, is group 1 more or less? And that's where we're looking. When I see differences, I'm thinking of ER words. Is it more dense, or is it denser? Is it softer or harder? Those are the way, every time I see differences or compare, I think of ER words. So I would say, well, group 1 are softer. Again, got that ER at the end. If I just say group 1 elements are soft, doesn't matter. It's not a difference. I have to say they're softer. I could say the other way around. I could say transition metals are harder, and that's equally as acceptable as an answer because it's still comparing. I could say group 1 elements are less strong. Now, no, that's not an ER, but it's different. So again, we could say the harder or the stronger for transition metals. Now, we talked about melting boiling points, so we could say group 1 have lower melting point. Again, that's the ER. You cannot say group 1 have low melting point. There's got to be lower melting points. And that is question 1, or question 1.3. Okay, so this is complete figure 2, and it's important because it has in bold figure 2, which means there's going to be a diagram somewhere, and we can see figure 2 just below. And it says, to show the electronic structure of an aluminium atom. And it specifically tells you, use the periodic table, which means if you look on the periodic table, you will see aluminium looks like this. Now, they haven't told you what to do after that. They haven't told you about electrons. They're expecting you to know that this bottom number is the number of electrons. And when they say complete, they mean you're going to have 2 electrons in that inner shell, because that's the most electrons can go in that inner electron shell. And then we have 8 in the next electron shell. And so left over are these 3 outer electrons, or valence electrons, in that outer electron shell. The next question is aluminium is a metal. Now, straight away I'm going, right, metal. What do I know about metals? Do I know the structure? Do I know the properties? A big property of metals is that they're soft, but the other big property of metals is that they conduct electricity, which is what this question's asking about, because it says they conduct electricity. And they're saying answer in terms of electrons, which means if you're not using the term electron, you're going to be missing marks straight away. Okay? Now, what do we know about electrons, or what do we know about metals with electrons? We know that there are delocalized electrons. Okay, now we can say they're delocalized electrons. We can also say that they're negative electrons if we want to, but it's important to know that the electrons are always negatively charged. And if we know that they're delocalized electrons, how does that impact upon their conducting electricity? Well, these electrons don't have a specific ion that they're attached to, which means they can move. And because they have that negative charge, we can say the charge can flow, or the charge can move, but we need to say where it's moving. Not just it wiggles around a little bit and goes anywhere at once. It goes specifically through the lattice. And again, they sometimes say structure, so we can say structure or lattice. Okay, and it's important to realize that you need to know for this question, like I said right at the beginning, of metal, what do I know? I know the structure. The structure is that lattice at the end, and the properties, well, part of the structure is having delocalized electrons, and that lattice and delocalized electrons allows me to be able to talk about it conducting electricity. The very last one on this is name the type of bonding. Well, as soon as I see bonding, I think there's three types of bonding. There's metal or metallic bonding, and ionic and covalent. And they're going to tell me. If it says name the type of bonding, it means they're either going to give me elements where I have to find them on the periodic table, or they're going to just say metal and non-metal, which is what they do. And this is a fact that you just need to know, that metals and non-metals always form ionic bonds. And so the type of bonding is ionic. Now, magnesium oxide is a compound formed. Well, magnesium oxide, I'm straight away, as soon as they give me a compound, I'm saying, right, what is it? Is it metal? Is it non-metal? What type of bonding is it? So straight away, I'm thinking bonding. And I know that it's a metal and a non-metal, so therefore I know it's ionic. I haven't even read the question, and I'm straight away saying it's ionic bonding. A compound formed from the metal magnesium and non-metal oxygen. Great, already know that. I've already talked about it being ionic bonding. And then it says, describe what happens when a magnesium atom reacts with an oxygen atom. So it then says this important bit, if you notice, they say this quite often, you should refer to electrons in your answer. Now the way I would do this is, they have said a magnesium atom and an oxygen atom. Now every time I see the word reacts, I think in my head, oh, there's an equation for this. So I straight away write down a word equation. It's not as quick, but it's more accurate. Word magnesium plus oxygen. And I think, what is that going to make? Well, magnesium plus oxygen is going to give me magnesium oxide. Again, that is the point to help me, because they're talking about a magnesium atom and they're talking about an oxygen atom, not a molecule, but an oxygen atom to form magnesium oxide. So now I think magnesium, right, magnesium is in group 2. What does that mean? That means it has 2 outer electrons. So my magnesium starts off as an atom, and it's going to lose 2 electrons to become magnesium 2+. I sometimes write it exactly like this. My oxygen, however, well, going back to the magnesium, I could draw it if I really wanted to. It doesn't say draw, it says describe. But if I wanted to, I could draw my magnesium atom out, and it would have 2 outer electrons, and then I could draw my magnesium again, and it would have 2+ charge, because it wouldn't have any outer electrons, or that outer electron shell rather would be empty. It would still have the electrons that are in the inner shells. It just wouldn't have those 2 outer electrons. We can see it's lost 2 electrons. What happens to our oxygen? Well, that we know is in group 6, and so we can do the same thing. We can look at, well, an oxygen atom, it needs 8 electrons in the outer shell, and it only has 6 because it's in group 6. It has 6 outer electrons, which means it's going to gain another 2 negative electrons and become O2-. Now, again, we could draw this. We could say that there are 6 outer electrons to our oxygen, and then we could draw it again, the oxygen ion, and this time it's got those 2 extra electrons, and we could say gains 2 electrons. Now that's part of it when we're describing, and from a description point of view, we need to be saying magnesium loses 2 electrons to become magnesium 2+, and oxygen gains 2 electrons. So this for me, or these 2 bits, are the essential bits to become oxygen -2 after our oxygen atom has gained 2 electrons. We've said that it's an ion being formed because we've written the ionic charges. We've talked about electrons. We've talked about how many electrons are moving for everything. And that is our 4 marks for this question. Okay, now this is a big 6-mark question, and I know sometimes people look at a 6 mark and think, oh, I can't do that, it's too much. But if we break it down, it can be doable. So sodium carbonate, I'm looking straight away and thinking that's an ionic compound. Reacts with hydrochloric acid. Now, reacts tells me there is a reaction taking place. Something is happening. And this time it tells me it's an exothermic reaction. Now, in my head, I'm thinking hot, which means energy, which means temperature. So straight away, I'm getting these words in my head of, okay, we're going to be talking about hot or energy or temperature at some point. The equation for the reaction is, and then it tells me this equation, gives me the symbols, gives me the state symbols, everything. And then it has, closer to the question, but still not there, a student investigated the effect of changing the mass of sodium carbonate. Now, straight away, when I see investigate or test, I'm thinking not just a required practical, but I'm also thinking variables. So if they change the mass of sodium carbonate, I'm thinking that is my independent variable. That is what I'm going to change, or what this student is changing. So they changed the mass of sodium carbonate powder, and they investigated the effect on the highest temperature reached. Well, that's what they're going to be measuring, the highest temperature reached. So what is that? That is our dependent variable. Now, if you notice, I've done that. I've looked at this, I've broken it up before I've even got to the actual question bit. Because if they're telling me about investigation and telling me about changing and the effect of things, it's important. Then it says, plan a method. Plan a method. Okay, plan a method for me means require practical. It means we've done it before, somewhere we have talked about this. Now, there's only one required practical that involves exothermic reactions in chemistry, and that is our polystyrene cup. Polystyrene cup with a thermometer in the top. We've got a lid on top as well. Okay. Now that's really important, because if I've got my polystyrene cup sorted and know in my head, right, I've got that practical, I've already worked out my independent variable, I've already worked out my dependent variable, and that's the rest of it. It says plan a method to investigate the effect of changing the mass of sodium carbonate powder, that's my independent variable, on the highest temperature reached, that's my dependent variable. So I'm just going to write those down. That's my dependent variable, independent variable. I've written them down, and I could say changing mass, and I don't want to have to write sodium carbonate every time, so I'm going to use the symbol that they've given me, and my dependent variable is the highest temperature reached. Now, why am I doing this first? Okay, it doesn't say anywhere in there write the variables. The reason why I'm doing this is for later on, really. It helps me ensure that my method is going to have everything in it that it needs. Because if I'm writing the independent variable and the dependent variable, I'm also going to be writing the control variables. Now, if we go right back up to this equation at the top, we have sodium carbonate as a solid. Well, we're changing the mass of that. We've talked about that in our independent variable. We then go to our acid, which is aqueous. We haven't talked about acid at all in either of the variables, which means we need to be talking about it with a control variable, because that's what we're adding together. It's one of our reactants. So the one thing that I can keep the same is I'm going to have the volume, and it's not just volume, it's going to be the same volume of acid every time. So I'm going to be doing this method a few times so that I can get accurate results and fair results. So it's going to be the same volume of acid, but what else could it be? It could also be concentration. Whenever I'm talking about a solution, I can always talk about concentration as well as acid. Okay, now I can also have the same starting temperature, but in reality I've got 2. That's quite good. I'm okay with that. Now let's get to our method. Well, method. What's the first thing we need to do? We're going to put something together in our polystyrene cup. So we're going to add acid. We tend to add liquids or solutions first, but we can't just throw a bit of acid in. We have to measure. So we're going to measure the volume of acid. Now, with the method, it's really important to know the equipment we're going to use. And the way to measure the volume of acid is using a measuring cylinder. I'm not going into massive amounts of detail. I'm just putting it in brackets to show that I know we're using a measuring cylinder. Step 2, got my acid sorted. That's great. What else do I need? Well, I actually need some sodium carbonate at some point. But before that, I'm going to measure the starting temperature. So I'm going to say add thermometer, and measure temperature. And again, I could write this a different way. I could just say write temperature, or measure temperature rather, and then put thermometer in brackets. That's not a problem. I've measured the temperature, I've measured the volume of acid. I now need to measure the mass of, and again, I'm not going to write the whole thing. I can write sodium carbonate because they've given that to me. A piece of equipment to measure the mass. Every time we are measuring something and using a piece of equipment to measure, we need to say what piece of equipment it is. We're going to use a mass balance. Now, you could bullet point this. I like numbers because it really helps me out later on. Okay, once I've measured the mass of sodium carbonate, I then add to the acid, and if we know this practical properly, we put a lid on. And put a lid on. Okay, now once we've done that, we wait. We wait until the temperature rises because it's an exothermic reaction. We don't have to say wait. All we have to do is measure highest temperature, because that's what we're waiting for. How are we going to know it's the highest temperature? Because the temperature isn't decreasing, it stops increasing. Okay, so we're going to measure the highest temperature. Now this is where the numbers come in, because if I have number 1 to 5, I have to write that again potentially, and I don't want to do that. So I'm going to say repeat steps 1 to 5. And why am I repeating it? Well, because I'm changing the mass, and I've only done one mass so far. So I need to say repeat steps 1 to 5 with different masses. Okay? Now, that tells me that I'm going to measure the volume of acid again. I'm going to measure the starting temperature of the acid. I'm going to measure the mass of sodium carbonate, but I've said with different masses. And I could say of sodium carbonate, just to be absolutely clear. And then I'm going to add the acid, or not add the acid, sorry. I'm going to add the sodium carbonate to the acid, and I'm going to put the lid on. I'm then going to measure the highest temperature and repeat. That's why I've got repeat with different masses. We haven't said necessarily how many masses. We haven't said absolutely everything, because when we say put a lid on, we could also say stir. Okay, some people get overwhelmed because they think, oh my goodness, I haven't mentioned everything. With a 6-mark question, you don't have to mention 45 different things. You just have to show them that you know the method, you know the equipment, you know the variables. Okay, if you miss one step, you're not going to get 0. So put it logically, numbered steps, and that will really help you out when it comes to writing a 6-mark question. Okay, figure 3 shows the line of best fit drawn through the student's results, and then got this graph, and it says determine the gradient of the line of best fit in figure 3. Use the equation. Well, that's even better, because they've told us that the gradient equals the change in highest temperature divided by the change in mass. It's always the change in y. So how do we work out the change? Well, we have to find this point, and if we travel along, so using a ruler normally, we get to this point, which I would write on here. I write it on here. Now I need to work out what that is. Well, 28 to 30 means there's a 2 different gap, and there's 10 of those. So every single little one of these lines is going to be worth 0.2. So this means it's going to be 28.6. I then do this line. Now that's only one line above. So again, I write it on here. It helps me out. Then I've got it on my graph as well. 22.2. I then follow my graph down. That's easy. That's 5. And then I follow my graph down on the smallest one, and that's easy because that's 1. Now if I use my equation that they have given me already, I'm going to be writing 28.6 take away 22.2 all divided by 5 take away 1. And that is going to equal my gradient. Now we can write it underneath, or so I'm going to write it underneath so we can see. If I do those individually, I get 6.4 divided by 4 equals my gradient. And again, if I simplify that, or rather calculate that, 6.4 divided by 4 equals a gradient of 1.6. Okay, now that's only 4 marks because right at the bottom of this it says give unit, give the unit, and they've left a line for that as well, so they're not going to trick you. If they need you to give the unit, they will leave that space and say unit. Now how do we work out, because we've never seen this graph before? Well, if we look back to our gradient equation, it's the difference or change in y divided by the change in x, which is what our gradient is. So for the units point of view, it's y, the change in y, which is degrees C, divided by the change in x, which is grams. So we can write it as degrees C over grams, like that. Or what we can do is we can write degrees C divided by grams, or we could write degrees C grams to the minus 1. All of them are exactly the same. We tend to use that second one in the middle, degrees C divided by grams, and that's our answer. Okay, next question. It says the initial temperature of the reaction mixture is where the line of best fit would meet the y-axis. So that's if this is going all the way back here somewhere. Okay, determine the initial temperature of the reaction mixture. Well, actually that's exactly right. Show your working on figure 3. So what do we need to do? Well, to show our working, we need to actually draw something, because it's not just determine, guess a number. So what we need to do is we need to get our ruler and draw a straight line, as straight as we can, back to the y, or the y-axis, and that will tell us our number. So if I've drawn it correctly all the way back, which I know I haven't, okay, because I don't have a ruler, I'm going to draw it back, and that would actually be, should be 20.6, okay? And that's our answer. They're asking you to do, they haven't put it in the question, but they're asking you to extrapolate. They're asking you to go forward all the way backwards to that y-axis. Now, next one. Another student repeated the investigation but added sodium carbonate until the sodium carbonate was in excess. For me, I'm looking for that word, excess. Excess means too much. Okay, what does too much mean? Well, there's a required practical in this exam, or for this exam, which is all about excess, and I need to know that it's too much, but I also need to know there's going to be solid left over. So I'm going to see solid at the bottom. It just helps me remember, oh yes, okay, I know what excess is. It then says, which sketch graph shows the results obtained when the sodium carbonate was added until in excess? Now, again, what does excess mean? I'm circling it again because I know loads about excess. It means the reaction is done. The reaction is finished. It's not on its way to finishing, but if I have solid left over, it means the reaction's completely finished. Okay. Now, how do I know which one it's going to be? Well, if we describe A, the temperature, as the mass increases, the temperature increases, and then at a certain point, the temperature shoots up. Well, if I'm finishing my reaction, the temperature is not going to shoot up really high. So I know it's not that one. Okay, for this one we have, as the mass increases, the temperature increase, or the highest temperature increases forever. Well, if it's increasing initially because it's of the reaction happening, it's not going to go on forever if the reaction is already finished. So it cannot be that one. Now, process of elimination, it has to be C, but actually if we talk through it, the mass of sodium carbonate is increasing, the highest temperature is increasing. We know that happens for all 3 graphs, but for this one, we have a bit on the end where the temperature stops increasing. Well, we have to know, and we have to understand that the only reason the temperature is increasing is because a reaction is happening. We know that excess means a reaction is finished, so therefore the temperature is not going to increase anymore. So it must be C. Now, right at the beginning of the question, we worked out that it was an exothermic reaction, and now it says figure 4 shows a reaction profile. Straight away I'm thinking exothermic, endothermic reaction profiles. There's certain words I'm going to need to be using for this reaction profile. It's going to be about energy, it's going to be about activation energy, okay? It's going to be those important terms. We might be using reactants, we might be using products as well. And then we look at this. We got the diagram. We don't have to draw it this time. But question 2.5, what do labels X and Y represent? Well, I already know that I'm going to be talking about energy, and nowhere in this graph so far does it talk about energy. So if we look at reactants, the line of the reactants is there, and then as we go up, that big sort of hill goes up and then goes all the way back down to products. What are we always talking about? We're talking about energy. So therefore, X must be energy, because the energy of the reactants and the activation energy as it goes up. But they haven't asked us for activation energy this time. They've asked us for what do we call the difference in energy between the reactants and products. It's not activation energy. This is our activation energy up here, and they know that students are going to think energy, activation energy, and they'll leave it there. But what is the Y? Well, it is the difference between the energy in the reactants and the products. So we can call it the change in energy, or the overall change in energy, because the reactant's energy is here, it goes down, and now the product's energy is down here. How much did the energy go down by? That's Y. That's our change in energy. And now the last question. How does the reaction profile show that the reaction is exothermic? Well, exothermic, I know, means what? I know we're going to be talking about energy, and I know we're going to be talking about temperature at some point. And at this point, you need to think this is all part of one big question. The first question was the required practical. We talked all about temperature change. That's why we use thermometers. We then had a graph where we talked about temperature change. Okay, and now we've got these question 2.5, 2.6. We don't have temperature in this. We have the energy profile, or the reaction profile, where we're talking about energy. So we can almost think, right, I've done temperature. I've done a lot of temperature, so it might still be about energy, especially when it says use figure 4. It's not saying guess, tell me your best guess. It's saying use figure 4, which means I need to be looking back at figure 4, this reaction profile, and asking myself the question, what does that talk about? Does that talk about temperature? No. So I know I'm not going to be using temperature, but it does talk about energy. So I'm going to be talking about energy. And we've talked about the reactants, we've talked about activation energy a little bit, and we've talked about Y, which is that change in energy. All we now need to say is, how does that relate to being an exothermic reaction? And we can say the energy of the products is less than the energy of the reactants. Now, I've put it that way around quite easily, meaning the exact same thing. You could say the energy of the reactants is more than the energy of the products. That would be equally as valid. Okay, I always look at this first line of a question. It's going to tell me a lot about that whole question. This question is about different forms of carbon. Now, as soon as I see different forms, without reading on, I think allotropes. Okay, now I know it seems like a crazy word, but for me, different forms of carbon means I'm going to be talking, or this whole question, not just the individual bits, but the whole question at some point is going to probably talk about diamond, or graphite, or graphene, or the last one, fullerenes. Okay, it might not talk about all four, but it sets my mind going, right, I know that this is what it's going to be about. So if the question doesn't make sense, I'm coming back to these. Then it says figure 5 represents the structure of diamond. Tick, we're doing diamond. And it tells us that those little lines, or rather little dots, are carbon atoms. Now, for me in my head, I'm going, well, what is that other line? What do the lines mean? Well, I'm going for it. They are covalent bonds. Okay, that's part of the structure. They're covalent bonds. That's excellent. Covalent bonds sets me on the right line. We're talking about diamond. We know that they're covalent bonds. And the first question says describe the structure and bonding of diamond. Structure, what does it look like? Bonding, how is it all put together? So for the structure, I'm thinking, well, what does it look like? Although I've got a diagram, it's not a perfect diagram. I know that if it's got a name like diamond, it's going to be a giant covalent lattice. Okay, the giant, because it's really big, you can see there's lots and lots of atoms there. It's covalent because we've already worked out those lines are covalent bonds, and it's a lattice because there's the repeating structure throughout this thing. So that's my structure done. It's giant covalent lattice. I then get to the bonding. Well, you might think I've already talked about it because I've said covalent, but we need a bit more information about that covalent. So I'm going to say it's strong covalent bonds because they are strong. And whenever we talk about bonding, it's always useful to say if these bonds are strong or if the forces are weak. But also, they've given me a diagram which is not necessarily helpful. It's partially helpful, but if we look at each of those carbon atoms, we've got to think, why have they given us a diagram? If they've identified the carbon atom for us, we're going to have to be using the diagram. So if I look at one of this carbon atom here, and I know that the lines are covalent bonds, how many covalent bonds or lines are coming out of that carbon? I can then look at another one. How many covalent bonds are coming out of that carbon? I can look at every single carbon, and there are always 4. So I can write that there are 4 strong covalent bonds. That's my structure done. That's my bonding done. And that's it. 3 marks for it's a giant lattice, 1 mark for saying there are 4, and another mark for saying that they are covalent bonds. The next question down, explain. If you notice, that's just describing, it's stating facts. This one is explain why diamond has a very high melting point. So we're going to have to be talking a little bit about the structure and the bonding, but also why does that matter? Okay, so again, we can say the same thing as above, and this is where it becomes a little bit confusing because people think, hold on, I thought I'd just done that. Well, we're doing it again because it's still part of it. This is the description bit. It's a giant covalent lattice, and it's got 4 strong covalent bonds. Okay, but now comes the explain bit. Why? Why does that matter that it has 4 strong covalent bonds? Well, the explain bit is it needs or it requires a lot of energy, and you can't just say it requires a lot of energy, because what you need to do is say, what is that energy doing? What is the energy going to do? It requires a lot of energy to break the bonds. Those strong covalent bonds are being broken. Okay, again, we've got this first sort of sentence before we get to the question. Figure 6 represents the molecule C70. You'll think, oh, might have seen that before. We can also go straight into the same part of the dots represent carbon, the lines represent covalent bonds. But we'll get to the question. What is the name of this type of molecule? Well, the whole point of listing in our heads, or writing it down, that allotropes of carbon are graphite, graphene, diamond and fullerene, is this question is all about those. The previous 2 were all about diamond. So we can almost tick those off and go, well, it's not going to be diamond, is it? If you notice, that's not an option, okay? But we should know that graphene is layers, or an individual 2D layer. Well, that's not 2D, is it? Or a layer, okay? A nanotube, well, it's got the word tube in it. It's not that, okay? And a polymer is a long chain of things, okay? But even if you're thinking, I don't know what polymer is, you've got these 2 options. You've got rid of the nanotube and the graphene because you know that it's not those, and you've got in the back of your head, we're doing allotropes of carbon. Well, a fullerene is an allotrope of a carbon, so it's going to be that type of molecule, okay? And then it says molecules such as C70 can be used in medicine to move drugs around the body. Suggest one reason why the C70 molecule is suitable for this use. So it suggests one reason. Suggest, for me, is there's lots of reasons. Okay, there's not one right answer. You only get 1 mark for it, but there are lots of different answers you could give. And it's a suggest, okay? And it's only 1. You don't have to write 10 different ones. So, what is a reason? Well, if we just look at it for a second, looks a bit like a ball or a sphere. And if we look, you should remember that this is the only one that is a little bit weird, and it's hollow. There's lots of empty space in the inside. And when it says it can be used in medicine to move drugs around the body, what it means is put the drugs inside the middle and it moves around the body. Okay? We can also talk about graphite, graphene, diamond, that those if you eat them, if you sort of put them into your body, they're not going to kill you, they're not toxic. So you could also say it's non-toxic. Okay? Our allotropes of carbon are non-toxic. If you think you've ever stabbed yourself with a pen, or a pencil rather, always think it hurts, but it's not going to poison you, even though you might have been told that. So it's non-toxic, and as part of that, it's unreactive. Now, I've written 3 different answers. Like I said, you only need 1. Okay? Right, the next one. We have calculate the number of C17 molecules that can be made from 1 mole of carbon atoms. 1 mole. And then it gives you this. You tend to get given this in the exam. The Avogadro constant is 6.02 times 10 to the 23 per mole. What does that mean? It means if you have 1 mole of something, you are going to have 6.02 times 10 to the 23 of something. Well, our question, I've highlighted it. 1 mole of what? 1 mole of carbon atoms, which means if you have 1 mole of carbon atoms, you have this many carbon atoms. Right? And it's a big number. It can be a scary number, but in reality, I always like to sort of simplify it back to things I understand. Because it's saying calculate the number of molecules that can be made from that number of atoms. Well, I think, ooh, that's a big number. Let me simplify it in my head for a second. If I had 70 atoms, how many molecules could I make? Well, I can make 1 molecule. Well, 70 does not equal 1. So what I need to do is do 70 atoms divided by 70, because I'm going to put them all together to make 1 molecule. And just to be absolutely clear, if I have 140 atoms, and I know that the final molecule is going to have 70, that's why I'm putting my 70 on the bottom. If I have 140 carbon atoms, I'm going to make make a molecule with 70 atoms. That means I'm going to make 2 molecules. Okay. Now I've done that. You're not going to get marks for that. It's nothing to do, but it helps me understand the maths that I'm going to do. I've got a big number. I've got the number of atoms on the top, and I'm going to divide it by how many atoms go into that molecule. Well, the 70 atoms go into the molecule, so I have to divide it by 70. Which means my maths is going to be, the equation I'm going to use is 6.02 times by 10 to the 23 atoms. And I'm going to divide that by 70. Okay, instead of 70 on top, instead of 140 on the top, I put this massive number on the top. And if I do 6.02 times 10 to the 23, divide it by 70, I end up with 8.6, actually, I'm going to write it down here, 8.6 times 10 to the 21 molecules. Okay, this question is about zinc and compounds of zinc. I'm looking at this sentence and thinking, well, I don't know anything specifically about zinc, so I carry on. A student produces pure crystals of zinc chloride. Well, straight away, I'm looking at pure crystals and thinking, that's a practical. So, what is my practical? It's crystallization or making soluble salts. Well, there's 3 parts to this practical. It's excess, filtration. That's how I always think of it. Excess, filtration, and then the actual crystallization itself. Now, the reason why I do this again is I've got my practical in my head, and even if I just write down those 3 things or think of those 3 things, they're probably going to come up because that's the biggest part of this practical. So, produces pure crystals of zinc chloride. Now, that is not what we did. That is not what anyone ever does. By reacting zinc oxide with hydrochloric acid. You think, okay, I don't know that, but I do know excess, filtration, and crystallization. I do know how to make crystals. And that's the important bit to highlight because you don't want to get confused thinking, I don't know what zinc chloride is. The equation for the reaction is, so they give you this equation. If you notice, there are also state symbols. Always useful to think about. You start with your solid zinc oxide, and then your aqueous hydrochloric acid, and you're making your aqueous zinc chloride and your liquid water. And then we get to this is all before we get to the question. This is the preamble. Then we have the student adds zinc oxide to hydrochloric acid until the zinc oxide is in excess. Sort of almost think, bingo, I'm in there, I already know. Give one observation. Now one is obviously bolded, which means you only have to have one, but it also says observation. You need to know that observation is what you see. So you got to think, what do you see when you make an excess of something? Well, I don't know the color of this. I know copper oxide's black, but that might not be the same as zinc chloride. So I've got to be a bit more general. So how do I know I have excess zinc oxide? I'm going to say, well, I make a solid, and a solid remains at the bottom. So I'm going to make a solid, or C, not make, C, solid remaining at the bottom, or no longer disappears. Okay, sort of the same thing, so it's not a problem. You don't have to say both, but it means the same thing. No solid is disappearing. We get to the next question. Why is excess zinc oxide used rather than excess hydrochloric acid? Now this we haven't done. This is not specific to this practical, but you got to think, why did we use a solid in excess rather than something which was aqueous in excess? Well, we've ticked off excess, we've done that. Have we talked about filtration yet? No. Right, how do we use filtration? Filtration is removing a solid from a solution or a liquid. Well, perfect. Why do we use excess zinc oxide? Because zinc oxide is more easily filtered, or is easily filtered. We're talking about filtration. Shocker. Okay, so we can almost tick that and go, right, I've done excess, I've now done filtration, which means I'm probably going to be talking about crystallization next. So, name one other compound, and again, it's bold, one other compound that the student could add to hydrochloric acid to produce zinc chloride. We go, this is where your reactions come in, okay? They've used zinc oxide, and you think, how else? I need the zinc, but how else can zinc be bonded? Now it's really important, it's an easy slip up to make, to not think of compound, because one other is bold, but not the compound bit. And it's important to think that compound is not one element, it's two or more different elements. It makes it a compound. So we can't just say it's going to be zinc, because that's not a compound. We've got zinc oxide, which means we could say it's going to be zinc hydroxide, or we could say zinc carbonate. Both of those work. They're not an element, crucially, because we've looked at that compound and thought that means two or more different elements. Now our last question on this, describe how the student should obtain crystals of zinc chloride from a solution of zinc chloride. Well, bingo, that's your tick. We're talking about crystallization now. So how did we do crystallization? Well, we heated the solution. Okay, and again, that's why knowing this required practical is so important, because we've already got, well, we've got 4 marks really for how to do this required practical. If all we remember is excess, filtration, and crystallization, and how to do each step, we've got 4 marks. So we heat solution until. Now, we can say until it boils, but it's not as simple. We've got to add a little bit more really, because the whole point of us boiling is to evaporate some of that water. So we can say until it boils, but I would go one step further and until it boils and some water evaporates, because that's really the whole point of us getting the water or the solution to boil. That's our first step. The second step is equally as important. We then need to leave the solution to cool. And again, I sort of say to cool, but I always do this as a separate, not as a separate point, as a together, to cool and crystallize, because again, that's where our crystallization comes in. Okay, zinc chloride is also produced in a displacement reaction between zinc and copper chloride solution. So the equation for the reaction is, and you've got to think, right, zinc is an element here. This is how I'm thinking, because they've told me it's displacement. Now, a displacement reaction means you're going to be switching places. Something's going to be switching places, which means it's really important to look at what's the element, what's the compound, what's part of a compound, because our zinc starts as an element and it ends up as a compound, whereas our copper starts as a compound and ends up as an element. Now that's excellent. If all we do that, we can look at the chloride and say the chloride bit, well, that's a compound, and that's a compound. Well, that's not helpful, because I really only care about those parts of this reaction that change or switch places. So we don't care about the chloride at all. That's not important, because nothing's changing. It was a compound or part of a compound, and now it's still part of a compound. But our zinc was an element, and we've drawn that there. And then our zinc turns into a compound with ions, or an ionic charge of 2+. So now we have to think, right, our copper, we're going to put our copper here. We don't care about the chloride, but we are going to put our copper, and that has 2 chloride ions attached to it, which each chloride ion, I can say, right, chloride ion, I know from my periodic table that's going to be -1, and if there are 2 lots of those, that means it must be -2 altogether. So therefore our copper has to be +2. And if we look at the other side, we've got our copper as an element. It never has a charge. That's why it's useful to know it's an element. And we say it's a copper. Now, you can see straight away if it's a simple displacement reaction with no sort of changing of brackets or needing balancing equations or anything like that, they both got the same charge. Copper is 2+, zinc is 2+. It's a simple displacement reaction. And then it says, why is zinc described as being oxidized? Now, it's really important for this. Oxidation, or oxidized, comes as almost like a two-set. We have oil, rig, and it's really important we're talking about this. Okay, and you need to know that's oxidation is loss. We don't need to do reduction because we've already got to oxidation. So what is oxidation loss of? Well, it's loss of electrons. We don't ever sort of say that bit at the end. So we know zinc is being oxidized. So we need to say it loss of electrons, because all we're doing is saying it's oxidation. Oxidation is loss. But we need to say how many electrons. Okay. Now our zinc is going from a neutral charge to a 2+ charge. That 2 gives us all the clues we need. A 2+ charge tells us it is losing 2 electrons along the way. Now, next question. Zinc and copper can be used with another substance to produce electricity. Complete figure 7 to show how zinc, copper, and another substance can be used to light a lamp. And this is the specific bit, because they're giving you information and telling you what you need to include. You need to include and label the zinc, and label the copper, and label the other substance used. But they're telling you, by the way, just in case you didn't know, it's not a physics exam, so we're going to tell you that a circle with a cross through it means a bulb. Okay? Now, how on earth do you need to know this question? You might be thinking, I don't know what this looks like. I've never seen something that looks like this. Well, if we read it again, zinc and copper can be used with another substance to produce electricity. Now you've got to think again, it's not a physics exam, this is chemistry. Now when do we use or generate electricity in chemistry? Well, there's only one required practical that involves electricity really at all, and it's electrolysis. Now if you make that link and say produce electricity, that's electrolysis, it'll help you out here because you think, I know how to draw the setup for electrolysis. It might not look like this, but I know that if I draw a beaker like this, and if I draw it like this, I'm on a good way, because now it looks like an electrolytic cell. Now it looks like electrolysis is happening. And I've got to label some things. So what am I going to label? Well, we always have to label those massive things coming down into our solution, which are called electrodes. But they've told me I need to label zinc and copper. So I'm going to choose zinc on this side, and I'm going to choose copper on this side. Okay, now I've done that way round. It's not particularly essential to do that. You could have done copper and zinc. Okay, there is no polarity that they've noted down, so therefore they're not going to make you lose a mark if you've got copper on the other side where zinc is. Okay, now I just want to make sure that they know that I know this is called an electrode, so I'm just going to write it just in case. I know it's zinc, I know it's copper, but I'm going to say it's electrode definitely. So I can go, right, I've talked about zinc, talked about copper, now I need to talk about the other substance. Well, I'm using zinc and copper, but then I've got to think, I've labelled my electrodes, I could label the beaker, so I'll label my beaker, I've drawn that. So the last thing is what's this stuff? What's the solution? Okay, I don't know. Okay, they haven't told me, they've just said it's another substance. So our general term for the solution we use in electrolysis is again, tells you about electricity, but this time it's an electrolyte. An electrolyte is that substance with all of the ions in it, which allows electrolysis to happen. We need that electrolyte for electrolysis to happen in the first place. Okay, this question is about groups in the periodic table. Now this is fantastic for me because I think groups, excellent. I know that it's going to be group 1, group 7, group 0, or transition metals, because those are the groups I need to know. And then it says the elements in group 1. Bingo, ticked off. I know it's going to be about group 1 now. They become more reactive going down the group. So I can almost have in my head, as I go down, they are more reactive. I can write that down if need be. Rubidium is below potassium. They're giving me all the information I need. It then has, and this is the preamble, it then gets to the question. Rubidium and potassium are added to water. Okay, that's not the question, but it allows me in my head to draw this and think, right, that's my potassium or my rubidium. I think I didn't do rubidium, but I did do potassium. And just imagining that image of being added to water, we can start remembering all the different things that potassium did when we put it in water. Okay, we're not going to write it all down because we're going to just look at what the question's actually asking us. Predict one observation. Now again, it's not just the word in bold we're looking at the word after that as well. So one observation is one thing we would see. It shows rubidium is more reactive. Well, now we have to start thinking about this water. And what did potassium do? Well, it moved. Potassium moved. So what is rubidium going to do if it's more reactive? It's going to move more quickly. That's a nice one. What else did I see? Well, potassium disappeared. So what is rubidium going to do? It's going to disappear more quickly. Okay, we could also say things. I mean, these are things that we can see. We can also say, there was a lilac flame. Well, this might not have a lilac flame, but it's going to have a flame. And how is the flame going to be different? Well, it's going to be bigger. It's going to have a bigger flame because it's more reactive. Okay, we could start talking about melting. We could also talking about exploding potentially, because we know that potassium essentially exploded towards the end with the lilac flame. We could talk about the fizzing, but with fizzing, we don't just say it fizzes more, because what does more actually mean in this sense? And we can't say it fizzes more quickly. Fizzing, we have to say it fizzes more vigorously. Okay, so it's a bit of a difficult one. You can't just say it fizzes more. I would say it fizzes more quickly. Okay, and again, we could do the opposite way around. We could talk about potassium moving less quickly if we wanted to. We then come to the next question. Explain. Explain means I'm going to be saying because or therefore. I'm going to be linking something to why. Explain why rubidium is more reactive than potassium. And you can see what we've already written. We've got potassium, then rubidium, and we've drawn this arrow to show as we go down the group, and we've written more reactive because that's what they already wrote and told us in the question. We've just written it in a more diagrammatic fashion. Okay, now why is rubidium more reactive than potassium? You might not have talked about rubidium, but you should have talked about sodium. You might have talked about lithium. So we can talk about a few things. Rubidium is bigger. As you go down the group, the elements get bigger. So rubidium is bigger. Now you could, or you could say larger, obviously. You could say has more electron shells, because as we go down the group, we get more electron shells. Now, here we go. So what? If it has more electron shells, what does that mean? Well, that means there is more shielding. If there are more electron shells, that means there is going to be more shielding. And if there's more shielding, there is less attraction. And there's a less attraction between what? We've got to say between, and again, we're going to be as specific as possible. So we're going to say between the positive nucleus, because we want to make sure that they know that we know that the nucleus is positive, and the negative, and it's not just any old electron, it's the outer electron that we're talking about here. And that's why that being as precise as possible is helping us out. So there's less attraction between the positive nucleus and the outer electron, negative outer electron, sorry. And here's the explain why. Why do all of those things matter? Because if rubidium is bigger, and if you notice I've written Rb or rubidium, if it's bigger, if it's got more shielding and less attraction, it's going to more easily lose its outer electron. And again, we've got that. It's not just going to lose an electron, it's losing its outer electron. Now, what is really important for this question is the more. Actually, I didn't highlight that at the beginning, but more is so important because it's a comparison, which means you have to be saying more, less, bigger, smaller, more easily, less easily. You can't just say rubidium is big, because that's not saying why it's more reactive. Okay? Now, the last one on this is complete the equation for the reaction of rubidium with water. Complete the equation. Well, we're back to the rubidium with water. I think we didn't do rubidium, but we did do potassium. We did do sodium and lithium. So if rubidium and water joins together, what are we going to make? Well, we know there's fission, so we know that there's going to be hydrogen made, because that's always made. Okay? We then need to think to ourselves, right, well, what else is made here? We have rubidium left over, and we have oxygen. Now, the easy trap to fall into is say we're going to make rubidium oxide, but actually that's not the case at all. What we're going to be making, and this is why they're called alkali metals, is we are going to be making a hydroxide, because a hydroxide in water is what we call an alkali, or lots of hydroxide ions is an alkaline solution. So therefore rubidium hydroxide makes the water alkaline, which is why we call it an alkali metal. If you notice, they then put this sentence, it's not just complete the equation, it reminds us you should balance the equation. So we have rubidium, one on one side, one on the other side, great. But then we have water. Now I always try and go for the most complicated compound first and try and balance that first. So if I have 2 hydrogens on one side for my water, but I have 3 hydrogens on the other side, that doesn't work. So if I look at my most complicated, which is my rubidium hydroxide, I've only got 1 hydrogen there. So if I put a big 2 there, I get enough hydrogens to make 2, but now I have 2 more oxygens. So if I put a 2 there as well, I now have 4 hydrogens on this side, and I have my 2 hydrogens from my rubidium hydroxide, and the 2 hydrogens from my hydrogen gas. That makes my 4, and then I have 2 oxygens in my rubidium hydroxide. But that means now I also need 2 lots of rubidium as well. Now, if you notice at the beginning of the question, it was groups. We said it was going to be group 170 transition metals. We did lots about group 1. Now the noble gases are in group 0. This is another group. What is a correct statement about noble gases? Now, correct statement, that means it's going to be true. Okay, and what that means is there's going to be some in here that are tricky, that are close to being true but not quite. Okay, now the noble gases all have atoms with 8 electrons in the outer shell. I think, yeah, that sounds about right. Not going to tick it yet though. I'm going to say, I think it might be right actually. I'm not even questioning it. I think that is right. The noble gases have boiling points that increase going down the group. Well, I know that boiling points generally increase as you go down a group. Okay. The noble gases have molecules with 2 atoms. Well, one property of noble gases I definitely know is that they don't make molecules. They exist as atoms, so I can cross that out. The noble gases react with metals to form ionic compounds. Well, again, like the previous one, they don't react really, they're inert, so we don't ignore that. We ignore that one, and then we come to 2, these initial 2. So we've got to think which is definitely correct, that we absolutely know. Okay, is it that the noble gases all have atoms with 8 electrons, or that the boiling points increase going down the group? Well, we now have to think, we only did the noble gases for the first 3, maybe 4 noble gases. We didn't do all of them. And we only have to draw a few of them from an electron shell point of view. We stop at calcium with 20 electrons, but we know that some of them have more electrons than that. So therefore we can't assume that all of them have 8 electrons in the outer shell, including helium. Helium is a noble gas, but it only has 2 electrons. So therefore actually we can say, wait, hold on, no, that is wrong. I've gone through, I thought it was right, and I've looked at helium and thought, no, wait, I know helium is a noble gas and that must be wrong. So therefore we come to boiling points. That's where it's really important. Don't just tick the first one you think. It's think through, and you'll get to usually 2. That'll be a bit close. And then you have to think through, what do you know? Well, you know how to draw helium. And helium doesn't have 8 electrons in the outer shell. Okay, table 1 shows information about 3 isotopes. Well, I see the word isotope and I think same protons, different neutrons. Straight away. I think that is really important, always important to know that by isotopes. And then it gives a table with a mass number and a percentage abundance. And it says calculate the relative atomic mass of neon. And this is the important bit. Give your answer to 3 significant figures. Okay, now how do we do this? Well, for me, I can write this whole thing out. I can write 20 times by 90.48, because that is 20%. The mass number is 20, and as a percentage, there's 90.48% of that. Okay, so I can write that, and I can do this, and then I can add 21 times by 0.27, and then add this to 22 times 9.25. Add all of that. That gives me essentially the total mass of 100% of this, even if some of it is mass number 20, some is 21, and some is 22. I then basically draw a massive line underneath it and say, and divide by 100. And if I divide by 100, the fact that they have told me, and this gives me this little hint, it says give your answer to 3 significant figures. So I immediately think, right, it's not going to be to 3 significant figures, it's going to be more than this. So what I'm going to do first of all is I'm going to write down exactly what I get, 20.1877. That's the full thing. Okay, I then go for, right, 3 significant figures. I've circled it, I've highlighted it, because I'm going to come back to it and just remind myself, what does that mean? Is that decimal places? No, because it would say decimal places. So 3 significant figures. So I need to count 1, 2, 3. Then draw a line, and then the 8 is bigger than 5. 5 are bigger, so therefore it's going to end up being 20.2. This question is about electrolysis. Now, alarm bells should be going off in your head. Good ones. Electrolysis. I think of a few things when I think of electrolysis. Funnily really, I think of panic. I see electrolysis and I think panic straight away. Positive anode, negative is cathode. It means every time I can remember that bit. And it just keeps me sort of on a level keel when I think about electrolysis, because when I think about electrolysis, it means I'm going to be talking about ions. It means I'm going to be talking about solutions, might talk about electrons, oxidation, reduction. There's a lot in here. Then it says molten, but this is where electrolysis sets my alarm bells for panic and ions. Crucially, I'm looking for words like molten or solution. It says molten. Molten means liquid. Doesn't mean it's dissolved in something, it means it's a liquid sodium chloride. So on the side I'm going, okay, it's got sodium ions and it's got chloride ions. I know it's going to be ions, and it said it's molten, it didn't say dissolved. So those are the only two ions I can have. It is electrolyzed in an industrial process to produce sodium. Never heard of it. Fine. Figure 8 shows a simplified version of the electrolysis cell used. That's fine. Now they've given you a diagram or a figure, which means you're going to have to use it and look at it at some point. So if we look through it, we're looking at panic. We've drawn the ions already, Na plus, Cl minus. Now we look at panic. I think, positive anode. So I think to myself, right, that's the anode. Then I think to myself, right, that's the cathode. Right, I've done my panic. Okay, molten. I've done my molten. I've done my Na plus and my Cl minus. Fantastic. And then I think, what's this mesh? I don't know what a mesh is. But I've got my chlorine gas at the end. Chlorine gas. So I'm going to write Cl2. Molten sodium. I'm going to write my Na. Na is coming out. Cl2 is coming out. And it means in here, in this molten sodium chloride, is my Na plus and my Cl minus. Now, looks a bit weird. I don't understand what it's doing. All I've done is done what I know already. Chlorine gas is Cl2. Molten sodium is molten sodium. Doesn't say ion, so it must be Na. I then get to the question. Which is the correct half equation for the production of sodium? Well, I've already written down here. I've given myself a massive clue because I've written down that the ion is in the sodium is in molten sodium chloride. So I'm going to start with Na plus. So I'm going to look for ones that don't start with Na plus and get rid of them. Well, that doesn't start with Na plus, and that doesn't start with Na plus. So I got rid of two already. Then I look for I'm getting Na at the end. That's important. Okay. Now, this doesn't help me. I've got two now. What have I got to work out? Is my sodium going ion? Is it going to gain an electron to go back to being sodium element, or is it going to lose one? Well, this is where it's important. My element is exactly as I draw it on the periodic table. So if I drew my element for sodium, I'd have one electron in the outer shell. Whereas if I drew my ion for sodium, it'd be +1, and it wouldn't have an electron in the outer shell. So how do I go from my ion back to my element? I have to gain that electron, which is why that is correct. So ion is adding or gaining an electron to go back to its sodium element. So it's essentially the reverse of what we usually do. Electrolysis is the reverse of making ions. Okay, we've got the diagram again. And again, the diagram is really important. We've labeled it previously. And then it says, a mesh is used to keep the products of electrolysis apart. Well, we know what electrolysis is. It's to do with electricity. It then says, suggest one reason. So remember again, it's got it in bold, but it's not just the word one, it's the word after it. So one reason. So why, we need to say why the products of electrolysis must be kept apart. Well, it helps if we think about what is going to be where. Well, we know that chlorine gas is coming out the top, which means there must be chloride ions, and they're probably going to be on that side. And we know that molten sodium is going to be there, which means there must be sodium ions on this side, because the sodium ion is turning into sodium. And then we've got to think, well, if we have chlorine and sodium together, if we put Na and Cl2 together, what does it make? Well, it makes sodium chloride, or NaCl, which is sodium chloride. And we don't want that because the whole point of electrolysis is to break that apart. So in reality, the reason is so the products don't reform. Bit of a different one, because usually you're looking at it's going to be an explosion or something like that, and there's nothing like that at all. We then have which type of particle passes through the mesh. So we have something going through the mesh in the electrolysis of molten sodium chloride. Well, the reason why we've labeled our diagram or our figure so well is because it's going to help us with a question like this. We've got our Cl minus, we've got our Na plus in the bottom, and then we've got our elements at the top. Well, that means it's not going to be an atom because the ions are in the bottom. It's not going to be an electron. It's certainly not going to be a molecule. We've already written Cl minus and Na plus, which means it's going to be an ion. And that's how we work it out. It's really important to use the figures because they help with a lot of the other questions. Now it then has, again, it's looking for these sentences which are in between the questions almost. Aqueous sodium chloride solution. Well, aqueous, every time I see aqueous, I think water or H2O. Aqueous sodium chloride is electrolyzed in a different industrial process. Two gases and an alkaline solution, right? Alkaline, every time I see alkaline, I think OH minus are produced. Which two ions are present in aqueous sodium chloride solution in addition to sodium and ion? Well, every time I see aqueous, I think water. So what I do is almost this. I think positive and minus, right? What's going to be in it? Well, sodium's positive and chloride is negative. It's saying there's an alkaline solution, and that's why every time I see alkaline, I think OH minus, because that helps me. And I think, well, what else is left? Have I talked about water yet? Well, I've talked about OH minus. I haven't talked about H plus. Now, if I do that table every single time I think about aqueous solutions being electrolyzed, straight away it says, don't talk about sodium ions, don't talk about chloride ions. What is left? Well, we have our hydrogen ion and we have our hydroxide ion, and that's our OH minus. Then it says, name the sodium solution produced. So we're sort of almost ignoring the previous bit where it's saying, ignore the sodium and ignore the chlorine. This time it's going back to, you've got all the ions, which is going to be produced? Well, if we go back to the top, it says two gases and an alkaline solution. And again, it says alkaline solution again. So every time I see alkaline, I think OH minus. So I know that my solution is going to have OH in it. And I also know that there's going to be two gases produced. Well, if I go back to my table here, and think which of these are going to turn into gases. Well, hydrogen ion turns into hydrogen, chloride ion turns into chlorine. They're both gases, so I can get rid of those straight away. And what do I have left? I've got my OH, which I've talked about already, and I've got my Na. If I put NaOH next to each other, that is an alkaline solution. That's pretty much the only one you need to know, sodium hydroxide. Now it then says, explain how the alkaline solution is produced. So you don't have to know the name to be able to answer this. You need to know how it's produced. And that's the important bit. And it says you should refer to the processes at the electrodes. So from a question point of view, I see alkaline. What do I think? I think OH minus straight away. And then it says, but it said solution, and I've worked it out. So I know I'm going to be talking about NaOH. But because it says alkaline, I know it's going to be an OH minus, which means my sodium is going to be an Na plus. It says you should refer to the processes at the electrodes. Now that's really important. They've given us a hint. Electrode. If I see electrode or see electrolysis, I think panic. Why? Because positive anode, negative is cathode. That means I can start talking about the electrodes by name. I can start talking about the positive anode. So I know that we're going to have sodium ions left, and I know that we're going to have hydroxide ions left. Okay, and now we're going to talk about, well, what is happening at each electrode? Well, if I draw my beaker, again, it's always useful to draw this because it helps you think about it. Okay, now if I have all of these, and I've drawn my table, so I've got all these different ions in solution, all these four different ions in solution, I've got to think what is happening where. Well, where is my sodium ion going to go? Well, my sodium ion is going to go to the negative. Why? Because opposite charges attract. But what else is going to go to the negative electrode or the cathode? The other positive ion is the hydrogen. and then my hydroxide is going to go to the positive ion, or positive electrode I should say, which is the positive anode, and my chloride ion is going to go to that anode as well. So we know that at the anode, positive anode, we are going to have a hydroxide ion, we're going to have a chloride ion, and we know at the cathode, again, I've done positive and negative above just for the charges, but this time we can talk about anode and cathode. We know at the cathode, we're going to have a positive hydrogen ion and a positive sodium ion. We then start talking what is happening, how am I making my NaOH? Well, what is going to happen to the chlorine, or the chloride ion I should say? Well, we don't actually need these. We know these are left over. These ions are left over. So we need to talk about really what is happening to my hydrogen. Well, when my hydrogen gets to the negative cathode, it's going to pick up an electron. And when it gains an electron, gain electron, we know what that's called. Gain electron is reduction, because we have our oil rig. And hydrogen ion plus electron makes hydrogen, except we already know it's H2. Now I've put a 2 there, which means I need to put a 2 in front of all of those. I've talked about what is happening at my anode, not my anode, sorry. I've talked about what is happening at my cathode, is my 2 hydrogen ions are gaining 2 electrons to become a hydrogen molecule. I can then talk about what's happening to my chloride ion. Well, I can label that, I can say that's going to happen at my cathode, and my positive anode, I have a chloride ion, and that isn't going to gain an electron, that's going to lose an electron, and it's going to turn into a chlorine atom. But again, we know it doesn't exist as an atom, we know it exists as a molecule. So if I've turned my chlorine atom into a molecule, I have to double everything else. But we know that our chloride ion is losing an electron, and losing electron, oxidation is loss. Oxidation. So reduction is happening at the cathode, oxidation is happening at the anode, and we have our ions left over. It's a lot in that 3 marks. There's a lot of things to know. You could write it as words. You could say that the hydrogen gas is being discharged at the electrode. I tend to do it as a half equation because it explains what's happening, and we get to use the word reduction and oxidation. Okay, this question is about silicon and compounds of silicon. Well, I'm reading this question thinking, well, I don't specifically know anything about it, but it then says the reactivity series. Well, reactivity series for me is thinking, do I know the order of reactivity? But also, whenever I talk about reactivity, I'm talking about extracting metals, so I'm going to be talking about extracting metals potentially, because that's when we talk about reactivity series. There's also a practical in there about reactivity series, or 1 or 2 practicals potentially, and the reactions generally are probably going to be displacement reactions. So I'm automatically thinking those 3 things. Then said silicon being extracted, right, excellent, we're talking about extracting maybe, by reducing silicon dioxide with different substances. The equation for one possible reaction is this, well, reaction, we might be talking about displacement as well. 2 lots of carbon react with 1 molecule, or 1 lot of silicon dioxide I should say, to make 1 lot of silicon and 2 lots of carbon monoxide. And then it says explain, which means there's going to be a because, or a therefore. Explain what this reaction shows about the position of silicon in the reactivity series. So we need to know this series. Well, if I look back at this equation, what is happening to silicon? Well, silicon as a molecule, or silicon as a compound I should say, is turning into silicon as an element. Well, why? Because my carbon is turning into a compound. So what I would say is silicon, well, I'd usually, in fact, not start with silicon, I'd start with carbon. So I would say carbon displaces, basically kicks out silicon from silicon dioxide. So I'm saying carbon displaces, well, that's not an explain, that's just an observation. I've just shown what I've seen really, that carbon is displacing silicon from silicon dioxide. I then need to say why. And that is because silicon is less reactive than carbon. And I could say that means carbon is more reactive than silicon as well. It means the same thing. Next question. Aluminium also reduces silicon dioxide. Carbon is used rather than aluminium to reduce silicon dioxide because carbon is cheaper than aluminium. Carbon can be obtained by heating coal, and aluminium is obtained from aluminium oxide. So again, we have this obtained. This is our extraction. Our extraction methods. We're getting back to extraction again. We're going to think, right, well, how? How is carbon? Well, they've told us it's hit by heating for carbon, but they haven't told us by aluminium. Well, we know, or we should know, that the extraction method from aluminium dioxide is electrolysis. Okay, that's an important part. That's why we get our minds thinking, right, extracting. What are those three ways of extracting? Is it by heating? Is it by heating with carbon? Is it finding in the ground on its own? Or is it by electrolysis? So what I would say is aluminium extracted using electrolysis. Okay, and that's my first mark because I've said how it is being extracted. But then I'm going to say, again, it's an explain. So I'm going to say why. So what? Well, aluminium is extracted using electrolysis, which uses a lot of energy, or a lot more energy, because it's more expensive than carbon is the question. So therefore, I have to say something about being more, not just a lot more energy. Magnesium also reduces silicon dioxide. We've got another equation, and we're looking at this. Well, magnesium is telling us that magnesium is displacing or reducing silicon dioxide, and we have state symbols. Again, give one reason why. There's not just one, it's one reason why. The products are difficult to separate if magnesium is used to reduce silicon dioxide. I think separation techniques. What do we have as our separation techniques? We have filtration, we have distillation, we have crystallization, all of these different separation technique, crystallization, all these different techniques we need to have. And every time you say the word separate, think, right, which one is it going to be? Okay, so why is it difficult to separate? Well, how are we going to know which one of these techniques to use? State symbols. Okay, so which of these methods of filtration, distillation, and crystallization separate two solids? None is the problem. Okay, and that's why it's difficult. So we can actually just say, well, why is it difficult? Because they're both solid. Which means we can't do filtration, we can't do distillation, we can't do crystallization, because they're both solid. Now, the next question, 7.4, it's a 5-mark question, which means it's a lot bigger as a question, because it's calculate. Calculate the minimum mass in grams of magnesium needed to completely reduce 1.2 kilograms of silicon dioxide. Now, there's a few things here. Straight away, minimum mass, okay, fine, of magnesium needed to completely reduce, they give me a number, 1.2 kilograms. Well, we don't measure anything in kilograms in chemistry. I know in physics we do, but in chemistry we don't. Which means we need to convert this. Now, 1.2 kilograms is the same thing as saying 1,200 grams, because I've timesed it by 1,000 to convert between kilograms and grams. Straight away, I get a mark. Silicon dioxide. Now, for me, I see relative atomic mass here. I see this bit. And if I see that, it tells me straight away you're going to be doing moles. I know I'm going to be doing moles. Okay, so I need to make sure I've got my moles calculation. So mass equals Mr. Moles. Okay, and then I think, well, I've got a mass here, so 1,200 grams. Do I have an MR for my silicon dioxide, which I've circled because that's where the 1.2 kilograms comes in? Well, silicon dioxide from our question right at the top here is SiO2. I don't have that. I haven't worked that out. So I need to work that out as being 28 plus 2 lots of 16. And that equals 60. Okay, now so I've got 1 mark for conversion, 1 mark for working out the molar mass. I can then use this formula. So I can then say 1,200 grams equals 60 times by mole. And then if I solve for mole, I can then do 1,200 divided by 60 equals the mole. Again, we're using this technique, this way of calculating, because it helps us quite a bit. And that equals the moles of SiO2 equals 20. So I've got 20 moles of SiO2. Now how does that help? Well, if we go right back to the top of our question, okay, they've given us the balanced symbol equation. I'm just going to get rid of some bits so we can look at it clearer. Okay, we have 2 lots of magnesium to 1 lot of silicon dioxide. Okay, those numbers in front give us that ratio. So straight away I know that if I have 1 mole of silicon dioxide, I'm going to have 2 moles of magnesium. Now I've got 20 moles of silicon dioxide. That means I need double that for this side. So I need 40 moles of magnesium. Okay, now that gets me another bit. I then use my mass equals Mr. Mole, so I'm going to do that again. Mass equals Mr. Mole. Because again, I don't have a mass because they're asking me to find the mass of magnesium. And so I'm going to say mass, because I don't have that, equals Mr. Now, do I have the molar mass of magnesium? Ah, yes I do, that's 24. And I have the moles, I've just worked that out. That's going to be 40 mole. And if I do 24 times by 40, that is the mass of my magnesium is going to be 960 grams. Okay, so it's going through systematically and using that formula. That formula is the most important one, because when they give you the relative atomic masses, you know you're going to be using that one. They've given you a mass, we've done conversions, we've worked out the molar mass for silicon dioxide, because they've already given it to us for magnesium. Now the next one, complete figure 9 to show the outer electron shells in a molecule of Si2H6. Never seen this before, okay? But we can say something. We have silicon in the middle, which is the same element, and we have hydrogens around the edge. So we need to make sure we get our dots and crosses in the right order. So our hydrogens are all going to be 1, and our silicons are all going to be different. So what I would do is I'd put a dot and a cross in all of my hydrogens to make sure that I've got a dot and a cross in each of these. And then I'd look at my silicon. Okay, well, what group is silicon in the periodic table? Okay, silicon is in group 4. That means it's got 4 electrons in its outer shell. And if we go around, each of our silicons only has 3 electrons so far. But we know that the silicons must be bonded together because their electron shells are overlapping. So we need to put 2 in the middle. And this is where it comes in, because it's the same element. And we've already used a dot and a cross on the outside. We're going to have to use one of those again. So I will choose a cross. It could all be a dot, and that would be absolutely fine. But it's got to be 2 of the same. Otherwise, it would show an electron coming from a hydrogen, which isn't the case. Okay. Si2H6 reacts with oxygen. The equation for the reaction is, and they give us this equation. Now, at this point, all I'm looking at is those ratios of 2 to 7 to 4 to 6. They're the important bits so far. And then it says 30 centimeters cubed of Si2H6 is reacted with 150 centimeters cubed, and excess. Excess means too much. I'm just sort of annotating as I go, thinking, right, excess means there's too much of oxygen. Calculate the total volume of gases present after the reaction. All volumes of gases are measured at the same temperature and pressure. Okay. Now, again, what have I highlighted so far? I've highlighted the ratio of the molar ratio between these reactants and products, and I know that excess oxygen or too much oxygen. So if I actually do it like this, 2 to 7, 4 to 6, okay? Now, it then says calculate the total volume of gases present. Well, gas, that's a state symbol, so I'm just going to check above, make sure. Well, the first one's a gas, and a gas. This one is a solid, that's not a gas, so I don't actually need that one. And H2O is a gas in this instance, so I'm only going to need those 3, okay? Now it's then saying I have 30 centimeters cubed of this. What I can do then is I can work out how much of oxygen I need to be able to react my 30 centimeters cubed. So how am I going to do that? Well, I've got my ratio, so I can do 30 divided by 2 and times by 7, and obviously that's essentially 30 times by 3.5, and that's going to equal 105. That's how much I needed. I don't have 105 though. They've given me this number of 150, so what I'm going to do is say, well, I had 150, I've used up 105, which means I have some left over. I have 45 extra. That's my excess. So I have 45 extra. Okay, now that's going 30 means I need 105, but also I can then say, well, from this 30, how much water vapor am I going to produce? So I can do 30, again, divided by 2 times by 6 is the same thing as times in by 3, and that equals 90. Okay, so now I know that I've got 90, I've made 90, and I know that I've got 45 extra. So if I do 90 plus 45, that's going to give my final volume of gas of 135 centimeters cubed. Okay, it's going back to this ratio. If they give you a balanced symbol equation with numbers, we're going to be looking at this ratio every single time. This question about acids and alkalis, that's the first sentence. You know, acids and alkalis, we are going to be talking about a few things. So before looking at the question, means this whole question 8, we're going to be talking about pH, we're going to be talking about H+, OH-, we might even talk about titration in there somewhere. Oh, we're going to be talking about neutralization, because that's part of it. Okay, we've got all the colours of neutralization, the colours of the pH scale if we use indicators. Okay, and obviously it says acids and alkalis, so we're going to be talking about acids and alkalis. Well, what do we know about those? Well, they can be strong or weak. All of this is before I read the question, because it's setting my mind up for this whole question about acids and alkalis. It then says explain why. So I'm going to say something and then say why. What does this matter? So why does the pH of an acid depend on the strength of an acid and the concentration of an acid? Well, we've got 2 bits there, haven't we? And it's worth 4 marks. I'm looking here, checking how many marks, which means I'm going to need to say, well, 4 marks like this means I'm probably going to be writing a paragraph of some sort or bullet points, and they're going to be checking, have I said a reason for the strength? Have I said a reason for the concentration? And have I said why? Okay, and now notice I'm looking strength, concentration, acid. Those are the 3 things I'm going to be talking about. Strength, concentration, acid. I can sort of tick those off as I talk about them. Okay, so what do I need to know? Oh, hold on, pH as well. Talking about pH, which means I'm going to be talking about pH too. Have to talk about all 4 of those things to get my 4 marks. That's how I'm going to get my 4 marks. Let's start with pH. What is, I'll say we'll do it in the order. What is pH? Well, pH depends all about the concentration of hydrogen ions. It depends on hydrogen ion concentration. That's the first thing. Okay. The higher the H+, the higher the H plus concentration, sorry, the lower the pH. Okay, I've said what pH is, and tick that off. I now get to talk about strength, or strength of an acid. Well, what is a strong acid? Well, I can actually label it like this and say I've talked about pH, now I'm going to talk about strength. Strength is strong acids, or stronger acids, dissociate more. So what? Again, we're getting this so what? Well, stronger the acid, have lower pH. How does that dissociation matter? Well, it affects their pH. Now talk about strength. Right, last one we've got to talk about. Concentration. Okay, what is concentration? Well, higher concentration, the higher the concentration of an acid, the more acid per decimeter cubed there is. More acid within a set volume of liquid. Well, so what? Well, the higher the concentration, you can see setting it out like this helps because it means we've got a first statement and then a so what underneath it. Higher concentration, a lower pH. We've done pH, we've done strength, we've now done concentration. And have we talked about acids? Absolutely, yes, we have. We've talked about acids quite a lot. And that's our 4 marks. Okay, a student titrated. We noticed, we said we were going to be about titration. We've got our titration here. 25 centimeters cubed of hydrochloric acid with 0.1 mole per decimeter cubed of barium hydroxide solution. We're getting numbers straight away, so we've got to think into our heads, okay, we're doing titration at some point. The student calculated the volume of barium hydroxide to be used in the titration calculation as 23.50 centimeters cubed. Explain why the student used a volume of 23.50 centimeters cubed of barium hydroxide in the titration calculation. So explain why. So we've got to say what. Well, how do we do this? That's our first question. What are we even doing here? We've got a table. If we have prepared our minds of titration, what do? We take that initial reading, then we repeat the titration a number of times, and as always, right at the end, we calculate a mean. So how do we calculate a mean? Well, first of all, before we calculate a mean, we have to look for anomalies. 23.45, that's good. 5.5, good. 5.5, good. 4.5, good. 23.9 is different. Okay, so we can actually say, we're going to add these 4 up. And then, what we're going to divide them by 4. So we can say this is we can say 23.9 is an anomaly. Okay, that's that first thing. We're always looking for anomalies. And then we're going to say, well, 23.45 plus 23.55 plus 23.55 plus 23.45. Do all of that and then divide that by 3. That equals 23.50, which is the value we wanted, we were explaining in the first place. Okay, they've set it out asking you to explain when in reality we're just talking our way through it. Now we have 25 centimeters cubed of the hydrochloric acid reacted with 23.50 centimeters cubed of the 0.1 mole per decimeter cubed of barium hydroxide solution. We've got lots of numbers here. Okay, the equation, they've given us an equation this time, and it says calculate the concentration of hydrochloric acid. Well, straight away I'm doing a table. What are the 2 we care about? Well, they want hydrochloric acid, so that's quite important. And they've also said in the bit of the question at the top, barium hydroxide. So that's the other one I care about. I'm going to write those at the top so I remember what I'm talking about. The very next thing is I look at ratios. Well, 2 to 1. That is going to be very important going forwards, okay? I then look at what I have and think, is there an equation? There's definitely an equation for titration. Titration equation is moles equals concentration times by volume. Okay, so I'm going to be looking for those three things. I can put it down here, mole, concentration, volume, mole, concentration, volume, and then I can fill in what I've got so far, okay? And there's 25 centimeters cubed of hydrochloric acid. Boom, I've got my volume, except I don't. Because it's not 25 centimeters cubed. Well, it is, but I need to convert it to decimeters cubed. So I need to divide it by 1,000 to be 0.025 decimeters cubed. And volume again, it's not 23.50 because I've got to divide it by 1,000 to be 0.0235 decimeters cubed. Straight away I've done something, okay? Now, do we have a concentration? Yes, we do. We have a concentration of barium hydroxide. So we've got 0.100 mole per decimeter cubed. Just doing this allows me to know that I have everything but the moles for my barium hydroxide, which means I can actually work this out. I can say moles equals 0.100 times by 0.0235, and that is going to equal a tiny little number, 0.00235. So I can put that in there just so I got it in my table so it sort of helps me, and those are my moles. Okay, now the next thing we need to do, if we've got a moles for one, we can do a moles for the other. Well, this is where my ratio comes in. I have a 2 to 1 ratio. Well, I've got my 1. That means I'm going to need to times it by 2 for this side. And I can say number of moles over here is 0.0047. 0 moles. And then again, I've got this side. I have my moles. I have my volume. This time I have to work out my concentration. So I have moles is 0.00470 equals concentration, which I don't have this time, and I have the volume, which is 0.025. Now again, if I do this and solve for C, I can work this out. That's going to be C, and if I actually calculate it, it's going to be 0.188 moles per decimeter cubed. And that's how we do it. Setting out as a table is going to allow you to see which bits you've missed. Okay, this is the bit we're looking for at the end, the concentration. Everything else is a step for us to get to that final value. Okay, another student titrated sulfuric acid with barium hydroxide solution. The equation for the reaction is, let me give us this equation. The student measured the electrical conductivity of the mixture during the titration. The better the conductor, the higher the electrical conductivity value. Well, I'm thinking, I've never done this before. Okay, they show me a graph. Well, I can look at this graph and I can say straight away, as the volume of barium hydroxide solution increases, the electrical conductivity decreases until it gets to a set value of, or set volume, I should say. So I could look straight away and say, oh, that's about 29 centimeters cubed of barium hydroxide, and it stops. Okay, that's without looking at what the question is. That's just helping me by looking at that graph. Then says explain why. So we're going to be saying something and then saying so what. Explain why the electrical conductivity of the mixture was 0. We've looked at that already. We've talked about that. That's this point here. Why was it 0 when the sulfuric acid had just been neutralized? Well, if we go right back to the beginning question, we were listing all those things that we were talking about. Well, neutralization was one of them. What does neutralization mean? They've given us this word, neutralized. Well, what does neutralized mean? Well, neutralized is when H plus and OH minus react together to form water. That is what a neutral substance is. It has no hydrogen ions, it has no hydroxide ions. They've all been used. They've all been reacted. Okay, so use the equation. So I know what neutralized is. It's telling me right there. It then says use the equation for the reaction. Well, this equation doesn't say H+, doesn't say OH- necessarily, which means I'm going to have to be using something else in there. Okay, now I've said it's H+ and OH-, but we know it's not because we have a sulfate, the SO4, and we have the barium, which haven't been used up. We've used up the H2, we've used up the OH, that's made our water. What do we have left? We have barium sulfate. That's this. Barium sulfate. We've made something. We're using our equation. And it also gives us a massive hint because it says refer to ions in your answer. Well, what ions? We got to think. Well, is it H+? Is it OH-? Are those the only ions? We can look at our barium sulfate, and the very first thing we look at, is it ionic? Is it covalent? Well, barium is a metal, and these are both non-metals. So therefore, it is ionic, which means we can talk about the barium and the sulfate ions, and we can use the word ions. Okay, so what are we going to say? Well, does it conduct electricity? No. Why doesn't it conduct electricity? That's what they're asking us. Why is it 0? Well, at 0, there are no H+ or OH- ions. Excellent. And then we have our barium sulfate, which we know is ions, but we have state symbols for a reason in an equation. It's not just for fun or we get bored so we write them. Our barium sulfate is a solid, and we know from our bonding and structure topic that if the ionic compound is a solid, the ions cannot move. So we can say barium sulfate ions are in a solid, so cannot move. Okay, it's going back to, do we know what neutralizes? H+ OH- makes water. Do we know what barium sulfate is? That it is ionic. Okay, now at 0 there are no H+ or OH- ions. We haven't asked the question why. Why? Well, they produced water. Okay, so if we look at our next statement, barium sulfate ions are in a solid, so cannot move. That so is the why. Well, they're in a solid, so what? That means the ions cannot move. Okay, in a solid is really important here. The student then added a further 10 centimeters cubed of barium hydroxide solution. The electrical conductivity of the mixture increased. Give one reason why. Well, back to our barium hydroxide solution. Solution means aqueous. Solution means we have barium and we have barium and hydroxide ions. It's our barium hydroxide, and it's a solution. We know it's a solution because they tell us it's a solution, which means all of these are an aqueous solution, okay? And if an ion has been dissolved or is dissolved in water, which is what aqueous means, that means that these ions can move. So we can say barium 2+ and hydroxide, ions can move. Okay, now all we've done is we've talked about that barium hydroxide solution.